Hi, welcome back to Mr. Chemistry. This is electron configuration Hassium, HS. Hassium happens to be element number 108. It has an atomic mass unit of 270. Okay, that means we have 108 protons in the center, because that's the atomic number. And since it's electrically neutral, they have 108 electrons. Now the neutrons, remember that neutrons are AMU minus number of protons equals the number of neutrons. So that's going to be 270 minus 108, which is going to give me 162 neutrons. So I can put 162 right there. Pretty darn snarly, I'd say. By the way, snarly is a new cool, in case you're wondering what that means. Okay, so S subshell can hold 2 electrons. The P subshell can hold 6 electrons. The D subshell can hold 10 electrons. And the F subshell can hold 14 electrons. We start by using the up-up principle, which states that the lower shells are filled first before the upper shells, and we use the diagonal rule. We're going to go down them these orange arrows until we run out of electrons. So we go 1s2, 2s2. See that? Just following the arrows down. Next arrow down, 2p6. And then 3s2. See how easy that is? 3p6. 4s2. 3d10. 4p6. 5s2. 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2. Okay, then we go 5f14, 6d6. When we don't need this 7p here, not yet at least. So now, orbital notation, which is Hund's rule. Fill up arrow in the first suborbit before you fill that down arrow in that suborbit. So like in 1s, be up and down, and in 2s, same thing, up and down. Here's classic Hund's rule. Up, 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 and then you go down, down, down. See that? Fill the up arrows first, and then fill the down arrows. All right, let's go ahead and let's fill this out here. It's going to take a while, since we do have 108 of these guys. That's a lot of arrows. It sure is. It is a whole bunch of arrows. But we will. Everything is amazing. So we're just doing this and just having some fun here. Taking our time so we don't make mistakes. That 6s is awful, kind of like hidden in there, kind of, you know. Well, you know, it's best I could do on that. These 4s are really spread out because there's a lot of typing in that material. Okay, we're doing pretty good so far. We're getting close to the end now. 5f14, then 6d6, and there's our last arrow right there going down. Okay, that's important to remember that last arrow, and I'll tell you why. Now, noble gas notation is intended to make this long electron configuration really shortened. So you put Rn as the nearest noble gas. You can't use Hassium, which is the one after Hassium, because it hasn't occurred yet, right? So use the one right before, and there we go. Pretty simple, and that's Rn right there. So that gives me, now, even though it's written in the order that you see it, 7s2, 5f14, 66, it's more correct actually to put it in numerical order, because when you do noble gas notation, you're trying to show the energy levels filling from the lower shells to the upper shells. That's exactly why they do it. Also, the guy who invented noble gas notation wants you to do it this way. Quantum numbers. Pauli's exclusionary principle says that no two elements can have the same set of quantum numbers. Yeah, you know, some of them, I don't know, some of them, these lanthanoids and actinoids seem to be coming across like they do a little bit, you know. There are exceptions to the May-Lung filling rule. Energy exceptions. They call the May-Lung energy exceptions. So it's the order in which you fill electrons. If you notice something's kind of funny about some of these videos, you might want to check the May-Lung energy exceptions. Okay, now, although Hassium looks like it's in the 7th period, remember it's in the D block. So D block is always n-1. This is going to be 7 minus 1, which is going to give me 6 for my principal quantum number. So 6 goes there. And since it's in the D block, the L value is going to be 2. The M value is going to be negative 2 in this case. And then, of course, this is going down. That last arrow is going down. See that right there? So that's going to be 1/2 negative. All right. Well, that's it for this lesson. You guys be snarly. I will see you back here at Musin Chemistry.